I want to show you something called the chain rule. The chain rule is huge. The chain rule takes everything you've learned and just makes it a lot better. So, for example, we can do cool stuff now. We can do this. Right? We can do this. We could say if y equals x cubed, we can find y prime. Right? What is it?
3x squared.
But this is hard for us. Sort of. What must we do to differentiate that function?
You have to expand.
Expand. So maybe you're saying that's not horrible to expand that, but it's kind of horrible. But what if I change it like, what if I make one small tweak?
That's horrible.
That'd be beyond horrible. I mean, you would be, nobody would get it right because you'd make a math mistake somewhere. I would too. Because that's just too big of an expansion. I mean, that'd take you, unless you use the binomial expansion, which you'd have to do, that would be a pretty big Pascal's triangle, right? And it would be pretty nasty. Okay, so we don't want to do that, right? Okay, that doesn't look like fun.
No.
Okay, we can do this. We can say the derivative with respect to x of the cube root of x. We can deal with that. What do we have to? How do we rewrite that to do that problem?
X equals 1/3.
Okay. Which equals what then?
1/3. X over minus 2/3.
Okay, so we subtract 1. And we could write that as a positive, we could write it as a positive exponent on the bottom if we wanted to, right?
Yeah.
But, so we can do that, but I double dog dare you to do this. What if we want to take the derivative of, let's say, the cube root of something like x squared plus 3x plus 1 quantity squared? Not only would that not be fun, we can't do it right now, right? And why is it, what is it about, I'm going to see if you can articulate this. What is it about the first example and the second example that we looked at that made them so much harder than the stuff we can do now? Okay, there's exponent, but I'm seeing people doing this. What's that mean? Parentheses. Okay, that's good. They're parentheses, and so there are multiple layers to this one, aren't there? Right? We've got a power function, just like we had here, but then if you peel away that outside layer, we've got a polynomial inside, right? So it's a function of a function. What do we call that, thinking back to past years? Oh, what do we call that? It's been a while. This would have been last year, year before.
Is that the g of f of x thing?
Yeah.
What does it start with?
Yeah, it starts with a C.
Complex
No.
function, complex math.
It's a well, it is complex. Composition of functions. Remember that?
Yeah.
We'll start talking more about that. But that, for now, all you need to know. I mean, from now on, what we want to be able to do, though, we're trying to shift gears, and we're trying to get from being able to deal with sort of one-step functions to functions of functions. And that's what the chain rule does for us, right? Okay, so to get there, though, we need to do something sort of conceptual at first. I want to be able to give you a mental model that works for what the chain rule is. And I think this is a pretty good one. If we think about, lost my notes. How could I lose them in this clean desk? Huh? What do I do? What the heck? They're used to this. That's what I've got to do. Right? Lose my notes in the lecture. Oh, here they are.
See, he's all nervous. He wants to go leave.
No, I don't want you to leave. I want you to learn some math.
I'm evaluating him.
No. Okay, so let's take this example. Let's take the example of a clock. Okay, here's what we want to do. I want to define the positions of the hands on a clock. So we're and specifically we're going to talk about the angular position. And I'll explain that more in a second. So let's let S equal the angular position.
Mr. Oya, this is being recorded, right?
Thank you for asking, it is.
Okay, cool.
That's your job after all. Angular position of the second hand. Let's let M equal, what do you think?
Slow a minute.
Angular position of
The minute
the minute hand. And let's let H equal, what do you think?
Out of the hours.
No, H, no, that's right.
Oh.
Okay, so what we want to do here is now we got to think about, we're going to do a little calculus. We're going to think about rates of change. So I want to know, can you tell me, and by angular positions, everybody understand what that means? So angular position means, you know, as they sweep out an angle, there's going to be, you know, there's the upright position, there's, you know, there's a different position, there's after 30 seconds, the second hand is straight down, etc., right? Okay, so what is this? Take a second and just think about that. What in the world does that mean? S represents the angular position of the second hand, and M represents the angular position of the minute hand. What do you think that could mean? This is a little kind of a new concept. What do you think? Yes, sir. Okay, it is. I mean, we could think about this as being a derivative, and that's one of our notations for a derivative. But remember that a derivative, and we just kind of started talking about it this way, a derivative always represents a rate of change, right? So if we say something like dy dx, sure, it's the derivative of y with respect to x, but we can also say it's the rate of change of the variable y with respect to the variable x, right?
Yeah.
So, you know, extending that logic, this is the rate of change of what?
Second. So
This, okay, the second hand, position of the second hand with respect to the minute hand. Okay, so we're really just asking about how fast is the angular position of the second hand changing with respect to the minute hand. And probably an easy way to think about angular change would be in whole rotate or whole revolutions, right? Okay, so how long does it take for a second hand to go around?
60 seconds.
Okay, how long does it take for a minute hand to go around?
60 minutes.
Ah, good, because for a minute hand to go around, that's a complete hour, isn't it? Okay, so now cogitate. Think about that. Cogitate. I want you to tell me, what is the, I'm looking for a number here.
So it's like 106.
Maybe, don't say anything, everybody just think about it.
Oh, yeah.
Think about it.
What?
Maybe. No, I'm not gonna tell you.
Wait, what was the question again?
Okay, the question, I want to know what this number is. I want to know what is the rate of change of the position of the second hand, and let's just say in revolutions, right? With respect to the rate of change of the minute hand,
Oh,
right? How fast is the angular position of the second hand changing with respect to the minute hand? Okay? Now think about something that's a little more, it's kind of a weird, we're talking about angles and things like that, but think about like a velocity, right? A velocity is a rate of change, right? Or we talk about a velocity being the rate of change of position with respect to time. So what are we really measuring? We're measuring how much is our position changing for a certain amount of time change, right? If we have a velocity of positive 60 meters per second, doesn't that mean we've just gone 60 meters in 1 second, right? Okay?
is it like 36 seconds?
Yeah, 36 seconds divided by 6.
Maybe.
That's
Okay.
60.
Talk to your neighbor. Discuss it. Talk to your neighbor a little bit. This is a tough one. Put your head together.
Yeah.
60 seconds.
Yeah.
Minute hand, 160.
160, yes.
Hey, think about that.
What's that?
Yeah.
Oh, yeah.
160 yes.
1
I got a
second.
different number.
Okay, what'd you get?
I got
Oh,
60.
60 is right.
Oh, we just
60 is right, but now, okay, but now why
I
is,
thought that was too easy.
why is 60 right? Okay, good, because, okay, here's how I think about it. Because every time that the minute hand goes around once, right, the second hand has to make 60 revolutions, right?
Okay, well.
You get the idea? Okay, so we could write it this way.
That was way simpler than that.
60 revolutions per one revolution, right?
Oh, true. 65
Make sense?
by 160, I got it.
Okay,
Oh.
so then what is, now extending that logic a little bit more here, what is dm dh?
Still same. Still same.
Is it?
Wait, no, quiet, let's figure that one out. Oh, wait, no.
Now we're thinking about an analog clock, which we don't have in here anymore, but just a, a regular old analog clock.
It would be 60
Same,
over,
60.
it'd be 60 times 12, it'd be 12.
I'd be 12. Why would it be 12?
Because it goes around 12.
Okay, because would you agree that the hour hand goes around once, hang on a second here.
Every
Makes one revolution every how many hours,
12.
right? Okay, so does that make sense? So the hour hand, now think about this, the hour hand is gonna go around the clock one time when the minute hand goes around how many times? No, 12, because every time the minute hand goes around, it's an hour, correct? Does that make sense? So the minute hand actually, I mean, it seems like it ought to be more before you consider it, but the minute hand really only goes around 12 times in the time it takes, in 12 hours, right? In the time it takes the hour hand to go around the clock once. Because the hour hand goes around the clock twice, right, per day, AM and AM.
Because it would be 60 times.
No, you're thinking of the second hand.
No, the minute hand, because it takes. For every hour it goes around 60
Oh, no,
times.
you're right.
No, for every hour, the minute hand goes around one time.
Yeah.
I don't understand
Wait,
my
I
phone.
The
don't
minute
get
hand.
that.
You're thinking of the second hand.
Yeah.
Second hand goes around
The
60 times.
hour hand will be
Right.
1, so that's 1 hour, and then it has to go to 2, and
Yeah,
then 3,
because
and
there's
4,
those
so it takes
notches.
12 hours to get around the clock.
Oh, I see. But then that would
Right.
change the second one.
Well, okay.
Because every 60 minutes, that thing moves
Reach
just
the
1.
top until midnight.
And so it has to go around 12 times.
I get it, okay.
I get what you're saying, Mr. Wilson.
Do you? Does everybody get that?
Yeah,
What hour hand are you talking?
Okay, so this, all I'm saying is this, right? Okay, so here's our minute hand,
Yes.
right? Here's our hour hand, that's a 1, right? So our hour hand just points right there. Would you agree that when this thing goes all the way around once, the hour hand has just moved that far?
Yes.
So it's moved how much of one revolution?
112.
1/12, right? So then this thing would have to go around, the minute hand would have to go around 12 times for this hour hand to advance all the way around once, right?
Yeah.
So it's 12,
Exactly.
right? 12 revolutions of the minute hand means 1 revolution of the hour hand. Okay, now here's the chain rule, and it's not a difficult concept. The chain rule is just saying this. What is ds dh?
Wait.
It's 60 times 12.
What? How do you get
Here's how I know. Because this is what the chain rule tells us. The rate of, listen please, the rate of change of the second hand with respect to the hour hand has got to be the product of the rate of change of the second hand with respect to the minute hand times the rate of change of the minute hand with respect to the hour hand, right? Because they're sort of piggybacking on one another, right?
Okay, wait now. Let's see.
Does that make sense? Now you can think about this. This will help you conceptualize that. So would you agree that for every time that the minute hand goes around, the second hand goes around 60 times, right?
Yeah.
So if the minute hand goes around 3 times, how many times did the second hand go around?
3 times 60.
3 times 60. If it goes around 100 times, it goes around 100 times 60, 100 times 60, right? Does that make sense? And so then if the hour hand is only going around once for every 12 revolutions, doesn't it have to be the product of those two rates,
Yes, it does.
right? Does that make sense? Because when the hour hand goes around, that is 12, right?
Okay.
Okay, so the rate of change of the second hand with respect to the minute hand times the rate of change of the minute hand with respect to the hour hand is what we were looking for. Now, algebraically, this is very convenient. Algebraically, do you see anything canceling there?
The minute.
Yeah. Yeah. Now, you get algebraically, those cancel. And so the chain rule, in a way, is really easy to apply because algebraically, it sort of simplifies into the rate that you're looking for. Okay? Make sense?
Yeah.
Okay. All right. So now that we've got an idea sort of conceptually what it means, I want to show you how we apply it. Okay.
Does that mean the second hand goes around the clock 720 times in the time that the hour hand goes around once?
Yep, in 12 hours, the second hand. It doesn't seem like enough, does it?
Too many seconds of our lives.
Yes. Okay. So here is the chain rule then.
Okay, sure.
Here is the chain rule. I'm going to write this in a couple ways, and honestly, using it is not that big a deal. It's just conceptualizing it's a little tougher. So the chain rule says that the derivative with respect to x of f of g of x, now that's a composition, right? A function of a function. Is equal to, okay, is equal to, what do you think? You tell me what you think the answer is going to be here. Okay, it's going to be f prime of g of x times g prime of x. Okay, now can we relate this to the clock example? This is like saying the rate of change, like let's say f of x is the angular function that tells us how fast the minute hand is moving with respect to the hour hand, right? G of x tells us how fast the minute hand is moving with respect, actually I did it backwards. Second hand with respect to minute hand would be f of x. G of x is minute hand with respect to hour hand, right? So if we want to know what's the derivative of f of g of x, so how fast is the second hand changing with respect to the hour hand, then we're just going to multiply the rate of change of the first pair times the rate of change of the second pair. You kind of see the analogy there? Okay, so let's look at an example. What if we have something like y equals the quantity x squared plus 3x plus 2 to the fourth? Okay, here's how you can think about this. This is a composition of functions, right? In this composition up here, which is the outer function? F of x is, right? We have f of hand. We don't know what hand is yet, but, oh, it's g of x. Okay, but at the outer level, I've just got f of something, right? Call it f of hand. Down here, I've got something, call it hand to the fourth, at the outer level. It's like peeling an onion. The outer layer is a power function. Peel that away, and the inner layer is a polynomial, right? So what the chain rule tells us is we have to do this in layers. We have to look at the first layer and say, well, what's our rule for the outer layer of the onion? What's the derivative of hand to the fourth? 4 hand to the
third.
right. Okay, so the outer one is going to be 4 hand cubed, right?
Okay, yeah.
Okay, what's hand? Well, hand, now we can look inside. It turns out that what's actually in here, which was irrelevant up till now, we haven't needed to know. But what was in there was an x squared plus 3x plus 2. But now we have to multiply and add another link to the chain. So that's hence the chain rule. So now we look inside and we say, okay, well, there's hand. What's the derivative of hand?
2x plus 3.
2x.
And that's our answer.
Wait.
Right.
I like that.
Yeah, it's not hard, but it's incredibly powerful, right? So we can do really difficult stuff with the chain rule. Sorry.
Do you need to simplify that?
Okay, do we need to simplify that? I mean, yeah, maybe. Yeah, I don't know. I mean, personally, I don't think you would need to.
Like factor the inside of the hand.
What could we do to simplify this? If the question said, write the answer in expanded form, then that'd be pretty nasty. We'd have to multiply, expand that out and distribute, but it really wouldn't do that, because think what now, most of the time when we're doing derivatives, what we're really trying to do is find the zeros of the derivatives. And to find zeros of something, don't we want them factored anyway?
Yeah.
Right? And so we would be sort of undoing our valuable work by expanding that out again most of the time, right?
Yeah.
Okay, so let's go back then to our previous example that we looked at the beginning of class. That one looked horrible, right? But we can do this one now. It's not that big a deal. We might have to rewrite it very slightly. Okay, so now, how am I going to rewrite this function so it looks like something I could do, first of all? Okay, so I could make this a 1/3, couldn't I? Right, so I could rewrite this as the derivative with respect to x of the quantity x squared plus 3x plus 1 squared to the 1/3. Could I go one step further? Okay, yeah, because if I take a power to a power, what do I do to the exponents? Multiply, right? If I have, for example, if I have a to the m to the n, isn't that just a to the m times n?
Yeah.
Right? Okay. So I could go one step further with this and say this is really just the quantity x squared plus 3x plus 1 to the,
2/3.
now it's easy with the chain rule, isn't it?
Wait. How did you get the 2/3? So we times 2 and 1/3.
Right, because I'm just taking hand squared to the 1/3
Oh, I
is the same as hand to the 2/3.
Okay.
Okay. So then my answer is what? By the chain rule.
2/3 hand
So I've got 2/3 hand to the
negative
-1/3
times 2x.
times,
2x plus 3.
derivative of hand is 2x plus 3. So if I did want to simplify this one a little bit, probably the only way I'd want to simplify this is writing it in terms of positive exponents. So this would look like what rational function?
2x plus 3 over 2.
But 2 times that, right? 2 times over
3 times x squared plus 3x plus 1
to the 1/3, right?
to the 1/3.
Same as a cube root. So if I wanted to, I could even write it like this. No, because the negative just means it's going to the bottom, right? The negative exponent means bottom, the 1/3 means cube root. Okay? Yes, ma'am.
Where did you get the 2 on top of out
That from
Okay, yeah, from up there.
the derivative of hand.
So, okay, I see it now.
Okay? And so that too gets multiplied by that on the top, right? Everything else is on the bottom. Scroll up. Right there.
Well, where did you get the 3 squared?
Because this, a minus 1/3, the minus means it's on the bottom. The 1/3 power means cube root. And then the 3 was already there because it was in the denominator. Okay? Okay. Let's,
We have 5 minutes.
okay, that's enough. So, so how about, okay, so now, how about this one? Now we can be tricky with this one. What if I have something like g of t equals -4 over 2 t t cubed minus 1 cubed. Okay, that looks like a nasty one. Is that a quotient?
No.
It's not a quotient, is it? What can I do with this to make it not a quotient? Yeah, good. So I could rewrite this denominator with a -3 power, right? So I could rewrite this as -4 times the quantity 2t cubed minus 1 to the -3, and now it's just a chain rule problem, right? The -4, what do I do with that?
Times negative.
Leave it out front, right? It's just a constant. I don't do anything.
-3 by it.
Yeah, so right, exactly. Then I'm gonna do, outer layer would be hand to the -3, right? So let's do this real quick. So what's g prime of t gonna be then?
12,
Hand to the,
-4.
okay, well what's hand? Turns out it's a 2t cubed minus 1. So we gotta multiply by the other link. It's gonna be what?
6t squared.
That's it. All right, so here's, how much time do I have?
3 minutes.
3 minutes, okay. Maybe we have time for one more. So what about this one then? What if I have the square root of sine of x squared plus 1?
Okay.
Okay, that's y, and I want to find y prime. How should I probably rewrite that initially?
1/2.
Okay, so I've got the quantity sine of x squared plus 1 to the 1/2. So, what's the outermost layer?
1/2 sine.
So I've got hand, well actually no, what's the outermost?
1/2.
It's a 1/2, isn't it? It's a 1/2 power. So I've got hand to the 1/2. What's the derivative of hand to the 1/2?
Negative.
1/2 sine.
1/2 hand to the,
-1/2.
okay, what's hand? Well, it's a sine of x squared plus 1. Okay, so now we gotta delve into the next layer. I'm gonna go ahead and just erase these as we go. So we erased that outer layer, didn't we?
Yeah.
Okay, so now, what's the next layer?
Times cosine, right?
Mm-hmm.
Oh,
But don't think ahead. I just wanna know what's the layer of the function.
Sine.
Sine of hand, right?
okay.
So what's the derivative of sine of hand?
Cosine.
Cosine of hand. Okay, so we're gonna multiply by, oops. We're gonna multiply by cosine of hand. What's hand? Well, it's an x squared plus 1, so we just did the next layer. Now we're gonna peel away that layer, and what do we have?
Then you times the 2.
Yeah.
Why did you do
Because there were 3 layers to this one, right? We have to keep going until we get to the center of the heart of the onion, right? So now we got derivative of x squared plus 1 is just, whoops, is just 2x. And that's our answer. Okay? How does the number of links in the chain rule relate to the number of layers in the function? Yeah, exactly. The number of layers dictates the number of links, right?
Yeah.
Okay, you got it.
Wait, that's a whole answer.
That's it. We could maybe pull the 2x out front, put the sign on the bottom, you know, the sign square, but that's it. I'm gonna do 2 things. We'll let you finish the lab and or work on the new Moodle assignment.
It's so
I don't think it really can retake it.
Well, even if I did retake it and it did too horrible, there's so many other things that you easily get. That's fine. Yeah.
Okay. Okay. Probably actually tomorrow. I think you guys will be maybe working on the 2.4 and 2.5 textbook assignments. So yeah.
Do you have like a cinnamon thing in here that makes it smell like cinnamon, or is it just naturally that way?
It's just naturally that way, I guess.
That's pretty awesome.
Yeah.
Ice. Luke, do you want to take a break? It came out blurry, right? Are we going to the computer lab?
We're here. The lab is here. I've got the Chromebooks, but we're gonna do this first.
I'll give it to Elton.
In the United States, like, 85%. Yeah.
Mr. Oya.
Yes.
Wait, you said you
We're in a
were in the
normal
middle?
standard class everywhere.
No, not, yeah, you're right. Thanks.
No. Are you just going to it right now? Are you serious?
I just have all of mine like standing on that.
Wait, no, that's right.
I actually took this.
Sort of.
They had a kid and they decided to get what? When is that paper due?
Let's say tomorrow.
Okay. No wonder.
That's good enough. That'll work.
Yeah. Oh, this is the helpful.